Welcome everyone. Welcome to Harvard with the Fundamental in Physics seminar series. It's the first seminar for the fall term 2023. We are very happy and honored to invite Professor Xiaodong from MIT. He will be speaking about this topic you see from the title on a unified theory of generalized symmetry. Let me remind the audience, please feel free to ask questions in the welcome Xiaodong directly.
Okay. Yeah, thanks, Julian, and thanks for the invitation. This CMC, this seminar series is actually very important, especially after COVID. It became part of our academic life. Thanks, Julian, for organizing this for all those years. It's really a great series. So I'm really happy to give a talk here. And so today basically is kind of a summary of some theory about this generalized symmetry. And in recent years, the generalized symmetry became a very important and active topic. As I do believe it may have a very wide application. And so today I will try to summarize some kind of general point of view, and also maybe describe a certain application to this. Okay. It turns out that this the general symmetry is have very close. Certainly, there's a lot of people study that in energy, but have very close relation to condensed matter physics. And so in condensed matter physics, people are interested in the phase of matter. So now we think the phase of matter can be divided into 4 types. One is a gapped liquid, and another is the gapped non-liquid. So here the liquid and non-liquid really means that whether the lattice, detailed lattice information survive the infrared property or not. And usually in quantum field theory, especially, people feel that the detailed lattice regulation is not important. So therefore, the quantum field theory usually describe a liquid phase. But if you start with a lattice system, so sometimes it can happen that the detailed lattice information survive at a long distance. And there's no way to get rid of that. So those are usually called non-liquid. And the example for non-liquid is a fracton. And but that's a gapped version. And there's a gapless version of both cases. There's a gapless liquid and a gapless non-liquid. The gapless liquid can be viewed superfluid or Dirac semi-metal. And the gapless non-liquid actually is a Fermi liquid. Fermi liquid is a gapless non-liquid. The way to see this is the following. If you study the low energy effective theory of a Fermi liquid, you find you need the infinite number of fields to describe this Fermi liquid. So today I'm basically talk about the lattice system. So the quantum system we study always have a lattice regulation, and I will concentrate on the gapped liquid and the gapless liquid. And the gapped liquid have a pretty systematic understanding, so we'll give a brief review of that. But the gapless liquid is very challenging to have a systematic theory. It turns out that the generalized symmetry may play a very important role here. That is, the gapless liquid have emerging symmetry, and those emerging symmetry can be generalized symmetry. So therefore, if you understand the generalized symmetry in a very systematic, complete way, we may be able to obtain a pretty complete understanding of a gapless liquid. But however, there's a complete understanding of generalized symmetry. Somehow it's related to the understanding of gapped liquid. So that's why we will first give a brief review of a gapped liquid. And the theory of a gapped liquid actually provides a unified theory for generalized symmetry. So that's basically the theme. So one of the example of gapped liquid is a non-trivial example. It's called the non-abelian quantum Hall states. And non-abelian quantum Hall states basically describe a 2-dimensional electron gas in magnetic field. And there we have a Landau levels. Okay. And then let's assume this chi n is a wave function of n field Landau level. If you n Landau level, there's a many-body electron wave function is chi n. Then Jane pointed out that the product of this Kn are also gap. Kn itself is a gapped state, have energy gap, gapped liquid. But if you multiply several Kn together, you obtain totally different many-body wave function. And there's some reason to believe this new many-body wave function is also gapped. In particular, for example, we can have K1 to the kth power and the Kn to the mth power. This is a wonderful many-body wave function. And if you assume this is gapped, then this particular gapped many-body state turns out to have a non-abelian topology order, have a non-abelian statistics. Actually, one can derive its effective Chen-Simons theory. The effective Chen-Simons theory for this particular many-body wave function turn out to be like for this one is SU3 level 2. And for this kind of many-body wave function, SU2 level 2. And so therefore, we can manufacture some kind of many-body states whose low energy effective theory is kind of a Chen-Simons theory, and which have a lot of interesting properties. And there's another way to obtain non-abelian quantum Hall states. It's using correlation function of conformal field theory. So actually, this part is a 1 over the Ci minus Ej anti-symmetrizes. This A is anti-symmetrization. It's a correlation function of Marana-Fermi operator. So using this Marana-Fermi conformal field theory, you can construct this using their correlation function, construct their wave function, construct many-body wave function, and this many-body wave function also have a non-abelian statistic. So actually in the 1991, so this two-way to construct non-abelian states is proposed. And so this is an example of a gapped liquid state. You can see it can be very interesting and very rich. Okay, so when you have such a rich liquid, this is just recently we have a paper with Timo about yes. Or this K. Yeah, take any integer. So actually, this exponent is not very important. They don't change this Chen-Simons theory. But however, you can see the Kn is anti-symmetric wave function. K2 squared is symmetric. It's not a Fermion wave function. So include another K1. So this one is totally anti-symmetric. So it's a Fermion wave function. And then this K2 to the cube, that's also anti-symmetric. So that's also Fermion wave function. And so this is a two-way to obtain these non-abelian states. Okay. Yeah, if you don't have K1, it's a bosonic. So if electron is a boson, this would work without K1. But the K1 is like a kind of like similarity. Adding actual K1 don't affect non-abelian statistics, but it affect abelian statistics. So there are some details. Yeah, and I just want to say that this particular, this wave function looks pretty artificial. How one realize that. And recently there's a experimental progress in the graphene. You have a graphene, multi-layer graphene. They have a ABC stacking. If you do this ABC stacking, you find in the magnetic field, the surface of graphene happen to realize a situation where several lambda levels are degenerate. When several lambda levels degenerate, those wave function can be realized, can be ground state. So that's the key. Because those wave function, like a K2 is a two field lambda level. It's contain electron in the higher lambda level. So therefore, if different lambda level have different energy, those wave function have a high energy is not good. But if first a few lambda level degenerate, and those wave function are good. Okay. Anyway, so I just want to say that because this reason the ABC is starting graphene, so this non-abelian state probably can be realized. But this is really not main topic of this talk. So here just give some kind of example, and then the key question is that you have this highly non-trivial many-body states, which realize some kind of a long-range entanglement or topological order. So what is the general theory for this topological order? So one way to probe a topological order is to put a topological order on this sphere, on the torus, or Gini-Riemann surface. Then we have a ground-state degeneracy. So this ground-state degeneracy is one way to probe a topological order. But however, a more detailed way to probe a topological order is using so-called fiber bundle on the moduli space. The moduli space is the space of a different gap Hamiltonian. You can change the parameter in the Hamiltonian, which can still have a quantum Hall state, can still have a ground state. And this different gap Hamiltonian give rise to moduli space. Then for every gap Hamiltonian, we have a vector space describing degenerate ground states. So that's a fiber. You're changing Hamiltonian, you get another ground state subspace, another fiber. Then you get a vector bundle formed by these degenerate ground states. So there's a belief that this fiber bundle over this moduli space of a gap Hamiltonian contain a lot of information. And although there's a belief maybe contain all the information. So therefore you can formulate a general theory for long-range entanglement using this vector bundle over a moduli space. Yeah. And so this is really one approach based on the ground states. And there's another approach based on excitation. Those ground states have a anion excitation, non-abelian anion excitation. So those excitation are described by modular tensor category theory. So we can also use the modular tensor category theory to describe this different topological order. So there's two different approaches. One is ground state based, another is a quasi-particle basis. Okay, and so because we are going to use it, so let me describe a little bit this modular bundle theory. So basically vector bundle over moduli space. So what is this theory to describe topological order? So for the vector bundle, most important thing is a connection. And when you're moving around a loop, this vector, this fiber may twist around, then there's a unitary matrix describing these connections. However, for this particular vector bundle over moduli space, it turns out that for every contractile loop, this connection is only pure abelian phase. It's a diagonal, just pure U1 phase. There's some reason to say that. And however, only for the non-contractile loop, we get a non-trivial non-abelian barrier phase. Then how to obtain non-contractile loop? So let's consider we have a system on the torus. Okay. Then we deform the Hamiltonian. Then this deformation path. They can get another system on the same torus. Okay. Suppose we deform the Hamiltonian in such a way that these two torus can be connected by some mapping class group representation. So that after mapping class group transformation, the two Hamiltonian became the same. We can connect them. So that's a way using mapping class group transformation, you can construct non-contractile loop over moduli space. And over this kind of non-contractile loop, we may get some non-trivial unitary matrix describing this connection. So from this, you can see that actually this connection in this vector bundle actually is given by this representation mapping class group. Yes. Okay, it's really the following. Yeah. Suppose this on the over contractile loop is not diagonal, not U1 phase. Okay. Then what happens is you can consider you construct a time-dependent Hamiltonian which go around this small loop. Okay. And then because this small loop is kind of perturbation theory, and there's in common physics or there's a literature, there's a way to approximate the periodic time-dependent Hamiltonian by some time-independent Hamiltonian with some effective perturbation theory. If this if this non-abelian phase is non-trivial, it's not U1, then that means there exists a perturbation which split ground state degeneracy. Ground state degeneracy. And then there's another input, that is the ground state degeneracy actually is robust against any local perturbation. So if you assume ground state degeneracy is robust against any local perturbation, then there's a small loop, contrast loop would have a project flatness. Yeah. So that is this is the argument. Yes. Yeah, exactly. So the input is that there's a degenerate ground state which is robust against any local perturbation. This is the input. Robust means you add any small perturbation, the ground state can only shift together; they cannot split. Yeah, the ground state degeneracy cannot be split; only shift together. And so that means you exist some many-body wave function which are globally distinct many-body state, but locally we look locally they identical. So this kind of famous property for quantum entanglement. Globally different but locally identical. This is possible when you have a long-range quantum entanglement. Yeah. So this is reflecting that. Okay. Local, yeah. Local production and small local. Don't have to be really small. I mean, it should be smaller than certain limit. You'll be fine because they won't close energy, will not close energy gap. So there's a finite radius of convergence. That's it. No, don't. So there's no lattice symmetry. Actually, here is no symmetry at all. So lattice can be random lattice. You can break any symmetry. So yeah, there's no need to be translinear, right? Yeah. So basically using this idea for this representation mapping class group, for example, for 2 dimension, we can choose space to be a torus. The mapping class group will be SL2Z. So therefore, for representation, so every topology order would correspond to SL2Z representation. But not every SL2Z representation corresponds to topology order. So there's a way, so there's also additional conditions. By studying those additional conditions, we can obtain the classification of a kind of topology order in 2+1 dimension. And so recently, we just make some progress. So we're able to classify this topology order up to rank 11. It means we have 11 type of anyon or non-abelian anyon. You know, the progress kind of slow. You know, at 2007 we got a classification for 4. 7 years later we have 5. Another 7 years we get a 6. But recently with computer help we jump from 6 to 11, and we may be able to get a 12. So that's my actually this I spent a lot of time during COVID. I tried writing those programs to get this 11. Okay, so so this is basically some kind of a general theory for the topology order, and so actually there's a topology order also have a holographic principle. We know that in the string theory there's a holographic principle. That is the boundary CFT is equal to bulk ADS gravity. Yeah, they kind of equal. So that's a duality. But the topology order, there's a holographic is slightly different. Basically means the boundary determine bulk, but the bulk does not determine boundary. So it's only one way. Okay. And more mathematically, it's really to say the following. Because in the bulk topology order, we have an excitation. And those excitations are described by this Brady diffusion category. On the boundary, also have an excitation, the gap excitation. And on the boundary, they are described by so-called fusion category. So no Brady. And then this boundary determined bulk really means that the boundary fusion category determine the bulk Brady diffusion category. And their relation is a kind of well-known mathematical so-called Greenfield center. But that's in lower dimension. In high dimension, maybe some kind of generalized fusion center. Basically, on the boundary, you have a fusion higher category whose center determines bulk. So this is a kind of so-called this topological holographic principle. In some sense, this holographic principle also kind of is a more precise description of anomaly inflow. So basically that this boundary fusion category was said to have a gravitational anomaly. And so what is a gravitational anomaly? Well, it's a center. The center for fusion category give you a Brady fusion category. And this Brady fusion category, this bulk topology order is a more detailed description of a gravitational anomaly. So this is a kind of using holographic boundary bulk relation to define gravitational anomaly. You know, typically the gravitational anomaly, like a perturbative one, is defined as a boundary for bulk gravitational transaminant theory. You have a gravitational transaminant theory in the bulk, then the boundary you have a perturbative gravitational anomaly. And then here we generalize a bulk transaminant theory to any topology order, you know, then their boundary can have any gravitational anomaly. In particular, they have so-called non-invertible gravitational anomaly. Because topology order usually is not invertible. You know, you have topology order. Then we don't have another topology such as after stacking, you can cancel the topology order. So many topology order cannot be canceled. And so it's not invertible. So using the general definition, the gravitational anomaly are usually non-invertible. And this is kind of important for the classification of a 3+1D topology order. Because for the 3+1D topology order, so how to classify that? Because the modular tensor category theory or this modular bundle theory would I just described classify 2+1D topology order. But for 3+1D, what is the idea? The idea actually is following. For 3+1D topology order, you have a particle and a strings. And somehow you can condensing all the particle. If a particle are all both sides, you can condensing all the particle to the boundary and to form a gap the boundary by condensing all the particle. Then the boundary will only have this string extension. You have a string only boundary. And so because the boundary bulk relation, the string only boundary actually determine the 3+1D bulk topology order. Then we can classify string only boundary. Then that's led to the classification of a 3+1D topology order. Then using this method, we find some surprising result. That is basically if 3+1D topology order have a particle and a string, if all the particles are bosons, then those kind of topology order are basically Diagram-Witten theory. They all described by Diagram-Witten theory of a finite group. And so that's led to some really gauge theory with some twist. However, if some particle are fermions, it's something a little more complicated, but not much more complicated. There's some kind of fermionic twist. Yeah. And so what I really try to say is that you know, right now we have a pretty good idea about what is a topology order in different dimensions. And we start to develop a systematic theory to classify those topology order in different dimensions. So the next thing we really want to do is to turn to gapless liquid states. Yes. Yeah. Yes. Okay. Yeah. So this the boundary determinant bulk maybe is very general, and we kind of believe it's very general, but we don't know how general it is. But the moment at this slide, we consider the gap the bulk, that's topology order, and the gap the boundary. Okay. And then when you can the gap the boundary, there's a lot of equivalence. So basically boundary have an extension, they may form a fusion, they actually describe a fusion category. Then we say that if a two boundary described by same fusion category, we say they are equivalent. So we don't distinguish their difference. So at this topological level, so the boundary are really characterized by fusion category. Then the bulk is the one higher dimension, the particle can also fuse and also break, have more room. Yeah, I'm not familiar. So it's like a 1+1 dimensional boundary, 2+1 dimensional bulk. Okay, so boundary have a fusion category. 1+1 dimensional boundary. The boundary is a one-dimensional space. You have particle, they can fuse. You have a boundary fusion category. They can fuse with a fusion ring and F symbol. And then the bulk will be this Brady fusion category, a modular tensor category. So then what really describes it that once you know the boundary fusion category, then you know the bulk Brady fusion category. So there's basically that's that's what you mean. Yeah. So basically, and this many-to-one map is really the dream field center. The dream field center just do this many-to-one map. You know, several different fusion category of the dream field center may have same dream field center. So this is for the gap, the boundary is in this sense in the dream field center. But however, I think that this holographic. So in this case, the boundary different bulk may be even more general than that. Even the gapless boundary may have that. Yeah, even gapless boundary may also determine bulk. But we don't know how. Yeah, this is something to explore. How general this can be. Yeah. Yes. Yes. Yeah. So given bulk, you may have several choice of boundary. So that's why the bulk do not determine boundary. But for the given boundary, somehow the bulk is can be determined. So actually, in this paper with Akia, we try to explore this from operator algebra point of view. You know, we have a boundary extensions like a boundary onions. You can create a pair of boundary onion onto onion using a string operator. Okay. Then this string operator have a algebra. The string can be connected, become longer string, and etc. Then it turns out that this algebra of a boundary string operator contain a hidden Brady diffusion category. So in a sense, you can using this operator algebra of a string operator, which create a pair of onion onto onion to recompute this Brady diffusion category in one higher dimension. So this operator algebra way is kind of like a derivation. We don't have a very general theory, but we do this calculation for some very simple boundary, some abelian case. It works. So we believe in general it also works. So from this may be a better way. The string operator of a boundary, their algebra actually already encode the Brady diffusion category in one higher dimension. So this may be a kind of, I think, is an important direction to really prove this. Try to prove this. No, because of the higher category, I think the people struggle with definition of higher category, and this dream field center is a mapping between higher category. So certainly at the lower maybe two category or some there's a more detailed study. Even higher category, the definition of category itself is one need to still struggle to come with a very precise definition. Yeah. But this structure seems there. Yeah. You based on physical argument. So this is really a story of a topological order. So then we want to switch gears. We want to have a systematic understanding of a gapless states. just like what we did for topology order, for gap the liquid state, there is a systematic understanding. Can we have a systematic understanding for gapless liquid state? And this is really a very challenge, and we don't know what to do. In some sense, for gapped liquid is topology. For gapless liquid, it's a geometry. So actually, we don't need to go to geometry. Okay. And but however, there's one idea is that usually for gapless states, there's an emergent symmetry and also exact symmetry on the lattice. But usually the gapless states at the low energy, there's a more symmetry than lattice symmetry. There's emergent symmetry. The standard example is like a one-dimensional lattice model of electron. So near one Fermi point, and you have another Fermi point, then the SU2 spin rotation symmetry became SU2 cross SU2 for right mover and left mover. So this is a typical example of emergent symmetry, more symmetry at the low energy. And what we learned in recent years in particular, that is the emergent symmetry can be very rich, can be group-like symmetry, can be anomalous, can be higher form, or higher group, or maybe non-invertible, and all these crazy things. So emergent symmetry became very, very general. Okay. And because emergent symmetry is so general, so that's make us kind of optimistic, making some brave conjecture. That is, maybe emergent symmetry can completely characterize gapless states. Okay. And because at the moment we don't have a general theme, so why not? We just make a bold conjecture and to see whether it's wrong or not. And so basically, if you collect all the emergent symmetry, the claim is that wishful thinking is that that's basically determine gapless states. So therefore, study of a gapless state became a study of a generalized symmetry. So this is basically what we try to do here. So by studying generalized symmetry in the full completeness, we may end up with a systematic theory for gapless liquid states. So, okay. So that's really led to this desire to obtain a unified theory for all those different emerging symmetry. So that is really the motivation. And so that's why this general symmetry really became important. Yes. Yeah. Yes. Yeah. Yeah, that's right. And so the example you give actually is have continuous symmetry. Okay. And when you have continuous symmetry and it's supposed to be, you'll see that it's supposed to be there's a Bragg diffusion category describing this U1 continuous symmetry. And and this Bragg diffusion also contains this winding soliton is there. And so I'm hoping this radius information maybe when we have this kind of Bragg diffusion category may be there. But at the moment I'm not so sure really because for continuous symmetry, this Bragg diffusion category would need to have a infinite number object. It's not a finite. And in particular, the flux need to be even continuous, not even discrete. So there's some category of that type. So I'm hoping once that theory develop, maybe one can see this whether this radius can be have some way to describe it there. And but actually the more serious example would be you may have some kind of system with a finite symmetry, finite emergent symmetry, but there's a marginal line of critical point. Yeah, that's maybe more serious. But I don't know whether when you have a marginal line, you have line critical, but that also mean you actually have a continuous symmetry. So this is also a very interesting question. So actually this became you can already have some interesting issue here. Well, the line of critical point always imply emergence of continuous symmetry. that's we don't know, but at least so I don't know whether this conjecture is right or not, but at least if you follow this conjecture, you get a lot of new thoughts, and then you can try to explore whether it's right or wrong, things like that. Yes. Yeah. I don't know. Yeah. So those are difficult. You know, I think this so-called local unit transformation is very important to define equivalence class of gap states. For gapless states, I have trouble. So this is a very serious question. I don't know how to define gapless phase. Yeah. In a more rigorous sense. I think that may be still open question. Yeah.
Here, during the later symmetry, but you're not saying one point.
I almost want to say 1-to-1 correspondence, but I'm not sure. So I leave some room of error here.
Say you want to do this CMC
yeah.
Supposed to know all the symmetry, the feedback, topological feedback of the symmetry, and also know the reasonable. But you want to bootstrap the CMC, but it does not mean that there's only one solution.
Yeah, there's more solutions. So actually, there's a maximum emergence symmetry. Usually, you have multiple solutions, but there's only maybe there's one solution with the same emergence symmetry as your initial input. But there are other more complex solutions, which have a more symmetry than your input. Yeah, so I will give example of that. Yeah, so when you have a maximum emergence symmetry, I hope it's 1-to-1, but maybe a few to 1, or maybe countable to 1. I don't know. So those are really this is really just a line for research, and I myself thinking it's a promising direction, but exactly how things will reveal itself, I'm not so sure, but need some investigation. Yeah, but maybe I don't know whether I can get there or not. But anyway, so let's consider this something simpler. It's an anomaly-free generalized symmetry. So the symmetry, generalized symmetry can be anomalous, anomaly-free. So let's limit ourselves to anomaly-free one. So what do you mean by anomaly-free generalized symmetry? Usually symmetry described by transformation. Anomaly-free means that you can gauge that transformation. But here we just have words, generalized symmetry. We don't even have a transformation. How to define anomaly-free is an issue. Actually, there's a way to do that. Basically say that a symmetry is anomaly-free means the following: if there is an existing system without symmetry, so we have a system without symmetry, such that this system has the following property. This system have unique gap ground state on any closed space of any homotopy type. So like in 2 dimensions, this system have a unique ground state on sphere, unique ground state on porous, unique ground state on genus 2 Riemann surface, and on all these Riemann surface. If such a symmetric system have this property, we say that symmetry by definition is anomaly free. So unique ground state. Now this sounds a little bit weird, but when you have a lattice, it's a very simple statement. The ground state is trivial product states. It's a symmetric product states, And I try to state using topology, basically try to avoid using lattice, using macroscopic way to specify this condition. But on the lattice, when you have UV regulation, it really means that the lattice ground state is a product state and have a symmetric product state. Okay, so when you have a symmetric product state, the symmetry, if symmetry allows symmetric product state, the symmetry means anomaly free. So why this is important? Because when you have unique product states, the excitation about this product states actually are symmetry charge. When you think about ordinary group symmetry, that's what we have. We have a unique trivial product states do not break symmetry. All the excitation can be grouped into representational group. They are charges. So therefore, once you have a unique product ground states, the excitation can be viewed as a symmetry charge. And those excitation are described by this some kind of fusion category. So this fusion category is called R charge. It's a fusion category describing excitations. Okay. So therefore, we can use this fusion category to describe symmetry. For the group, that means we're using the rep G to describe symmetry, using the conservation law, fusion ring to describe symmetry. So that is the idea. But in general, we can using the fusion category of charge. Okay. However, in n-dimension space, this fusion category is a fusion n category. But however, there's a lot of fusion n category. Not every fusion n category corresponds to a charge of anomaly free symmetry. Okay. And only some special subclass. This special subclass is called a local fusion n category. Means that mathematics means that has a fiber functor which go to this fusion category to the n vec. Some n vec is some trivial, is a fusion category describe a trivial states. Okay. Actually, I don't know what those mean, but local fiber functor really, I don't know. But the physical intuitions are following. So let's think about the SU2 symmetry. Then we have a spin 1/2 excitation, this doublet. If you break this symmetry, break SU2, then spin 1/2 became accidental degeneracy of two trivial excitation. So therefore, this spin 1/2 excitation with the SU2 symmetry is a one thing. But if you ignore the symmetry, it's a sum of two things, accidental degeneracy of two trivial excitation. And this is physical understanding of this fiber functor map something to something trivial. Okay. So it means that every excitation can be viewed as a accidental degeneracy of some trivial excitation. And so that means the quantum dimension of this local fusion category are all integer. When you have a fractional quantum, non-integer fractional quantum dimension, yeah, they cannot split like that. So they are not local. So things kind of like that. So that's a kind of physical understanding. So this basically establishes theory. That's this local fusion n category describing anomaly free non-invertible higher symmetry. Yes. Yeah, this became a trickier question, and I think I may discuss that later, and but probably I cannot really describe in this talk. We can chat, but later I will touch this topic again. Yeah. Okay, so if you apply this theory to 1+1 dimension, so what is in 1+ dimension, this anomaly free symmetry are supposed to describe the so-called a local fusion 1 category. So what is the local fusion 1 category, or 1 category with a fiber functor? Well, this is another math result. This half algebra. So I classify half algebra. I think there's some version, the weak half algebra. I think this is just half algebra, not weak version, just half algebra. Okay. And so that really says in 1 dimension space, the general symmetry is not even anomaly free symmetry is not described by group. It's by something slightly more general than group, something half algebra. So that's you can have some flavor. So what is this general symmetry means? Okay. And then certainly we want to know what is the anomalous version of half algebra. If anomaly free is half algebra, then what is the anomalous one? So that's a very natural question. Then in higher dimension, what is anomalous version of a local fusion higher category symmetry? So here I just want to make a statement that if you start with some kind of anomaly free symmetry described as a local fusion category, you can twist this symmetry to obtain anomalous version. You can require that your twist is invertible. You do some invertible twist, like a cocycle twist, to get some anomalous version. Then what is those twists you can make? it turns out that later I will come back to this. The twist is given by the so-called, we call those twists or invertible anomaly. The twist actually is a automorphism of a generalized dream field center of a sigma R. And the sigma is a de-looping, and the Z is a dream field center, generalized dream field center. We need to do de-looping because we want to promote the one dimension. But anyway, I will come back to explain this result. But I just want to say that there is a way to twist anomaly-free symmetry. And then you obtain invertible anomaly for certain anomaly-free symmetry. So that's give you some classification or general theory about anomalous symmetry. Yes. Yeah, here things are kind of generalized. So let's say using group. So we have a group symmetry. Then we know that anomalous group symmetry is given by cocycle, group cocycle, some twist. So group with some twist characterized by cocycle, and that's this pair describe anomalous symmetry. So I'm kind of using this language. So we have another symmetry described by this local fusion category. Then we just want to do whatever twist I can do, and with certain twist, some invertible one, and which give us another symmetry, another general symmetry. Then we call that anomaly. And the twist is such that if my fusion N category, local fusion category is a rep G for group, the twist happen to be cocycle twist, so we recover the group sense. But however, the theory is formulated in such a way that it's applied for arbitrary local fusion N category. So therefore, even for this more general symmetry, we know how to do anomalous twist. So this is already pretty far from the original anomaly, is ungageable, abstraction of gauging, and things like that. But I feel this actually just like this definition is reasonable. Later we'll come back to this. You can see it's more reasonable. So the latter result probably can be used. Yeah. Yes. It's a local fusion. Local means with fiber functor. It's a weak alpha algebra. Yeah, there's several versions. I'm kind of confused about. Yeah. Is that a weak algebra? Is that the quantum dimension always an integer? Yeah, and so here I think here the requirement, the quantum dimension always integer. It's not just a square quantum dimension integer. So it's a stronger. The quantum dimension should be integer. Okay, yeah. Yeah. It is the boundary theory, but the things that yeah, it's a name, and so actually I'm going to use name again. Yeah, you can call, so basically about gravitational anomaly is a, so invertible gravitational anomaly means it's a boundary for invertible topological order or invertible TKFT. Then from that, the boundary for non-invertible TKFT was called a non-invertible gravitational anomaly. It's just a name. Okay. And one can, one kind of objection, you know, I heard, yes, several people told me this is a bad name. And yeah, I could call that, I'm happy to call that a different name. And it's but this name is useful, and so we'll see. Actually, I'm going to use that very quickly. Oh. Oh, this is a thing. Okay, maybe let me just okay. So So actually, that's what I'm going to do. So actually, this anomaly-free symmetry I just described, and their anomalous twist of this symmetry is still not general enough. And so there's so actually the emerging symmetry can be more general. And so we try to describe this a more general symmetry theory. So actually this more general theory for the symmetry, which is beyond the anomaly free and beyond invertible anomaly, there's a lot of version. Okay, and one version is this isomorphic decomposition, and another is actually so-called non-invertible gravitational anomaly. So actually, we can view symmetry, generalized symmetry, as a non-invertible gravitational anomaly. And so this non-invertible anomaly became very important. It turns out that we are still thinking about whether invertible gravitational anomaly corresponds to symmetry or not. Maybe not. But yeah, that's a little bit of open issue. Should the generalized symmetry further to include invertible gravitational anomaly? I'm not so sure. But at least we feel non-invertible gravitational anomaly should be viewed as generalized symmetry. And this is this point of view is very general, and for us is very helpful. So actually, we are going to present this story. Then another point of view is that we can view symmetry charge, symmetry defect at equal footing. They both have a conservation law. We will combine symmetry charge, symmetry defect together at equal footing using conservation law to describing them. Then you also get a very general theory. And this very general theory turns out to be related to this braid diffusion n-category in the trivial width class. So that's also replacing group to describe this very general symmetry. Another way is to say the topological order with a gap over boundary. That can also be viewed as a way to describe a symmetry. So this basically is kind of holographic theory for the symmetry. So I will just go to this non-invertible gravitational anomaly. Just go this part. Okay. So symmetry really means we have a transformation which commutes with Hamiltonian. So that's just a usual way to define symmetry. But here we do something unusual. We restrict ourselves to symmetric subhilbert space. And so the subhilbert space which are invariant under all the transformation, all the symmetry transformation. Okay. So on one hand, especially when you study gapless system, restrict to symmetric sector is no big deal. You still have a lot of gapless feature there. We don't lose too much. But on the other hand, theoretically, all the symmetry act trivially in this symmetric subhilbert space. Then suddenly we don't have a symmetry. All the symmetry behave the same. They act trivially. And we couldn't distinguish the symmetry. But intuitively, we know that, especially for gapless system, those low energy stations, their dynamics is constrained by symmetry, even when after you restrict to symmetric subhilbert space. Okay, so this is really the motivation. Thinking this way, we may get a more general theory for symmetry. Okay. Yeah, this V is a total Hilbert space of a many body system. This Vi is a vector space on each side. Okay. So usually when you have a many body system with a lattice UV completion, the total Hilbert space contains this tensor product decomposition. Okay. So the existence of tensor product decomposition is called a free of a gravitational anomaly. So that's a link. So tensor product decomposition means no gravitational anomaly. But however, the symmetric subhilbert space do not have a tensor product decomposition. Yeah, because for example, Z2 symmetry, you consider Z2 neutral sector, and they don't have the tensor product decomposition. Okay, so this really our main motivation. The lack of a tensor product decomposition means gravitational anomaly. And from this symmetric subscale space, you can see the symmetry imposes this lack of a tensor product decomposition. So therefore, symmetry is a gravitational anomaly. That's it. So just a very simple thing, but it's very rough. And this gravitational anomaly is always non-invertible. Invertible gravitational anomaly don't have this property. Yeah. And so then using this topological holographic principle, that the gravitational anomaly basically is a boundary of topological order in one higher dimension. Then you can see that the symmetry connect to gravitational anomaly and connect to topological order in one higher dimension. So that's directly the relation. Okay. So actually in this paper, they studied this some topological order using tensor network, and they studied the boundary extension of this topological order. And they can indeed see that when you have a topological order, the boundary extension from some kind of Hilbert space, and this Hilbert space do not have a tensor product decomposition. Okay, and this lacking of this tensor product decomposition can be thought of. You have some symmetry, you restrict the cell to some kind of symmetric subspace. Then when you do this symmetric subspace, you can recover this boundary of a topological order. So from here, we see the boundary symmetric subspace and the topological one dimension higher, and the boundary Hilbert space. So we can see some connection. Yeah, so this connection is really say that the system with generalized symmetry can be fully and exactly simulated by boundary of a topological order. So this is really the physical statement. So whenever we have a symmetry, then you have some system with a symmetry. Then we claim that the low-energy dynamics of such a symmetric system can be exactly and completely simulated by the boundary of certain topological order. But however, there's a caveat, that is only the symmetric subspace can be simulated. The charged sector is not there. The boundary do not have a charge sector. The boundary only simulate this symmetric subspace. So this is basically the key point. That's how the Bob topological order describing symmetry in such a precise way. Yes. Yeah, you can view this as a gauging, yes. And so, but usually when you gauge, you get a dual theory. So nowadays, if you gauge a lattice model, you get a dual lattice model. And here is a little different. Yeah, if you're gauging, really the following: we have a system with a symmetry. Okay, you view a system with symmetry as a boundary for one higher dimensional trivial symmetric system in the product states. And then you gauge the bulk. And the bulk topological order is obtained by gauging the bulk. So this is a general way to do that. This also works for anomalous symmetry. When you have an anomalous symmetry, then it can be viewed as an anomaly-free symmetry in one higher dimensional bulk and with some SPD order. Then you gauge its SPD states, then you get a bulk topological order for anomalous symmetry. So this picture works. So this actually is the main motivation for this picture. But this picture works more generally. It's for any generalized symmetry. So all the generalized symmetry can be viewed this way. So this is really the key message. Yes.
What sense is that trivial effect models?
They are not, I think. So suppose in the symmetry breaking phase, okay, like Z2 symmetry and symmetry breaking phase, you have all spin up plus all spin down. Or maybe all spin up is the ground state, all spin down is not the ground state. The both ground states are product states. They are degenerate in symmetry breaking phase. Okay. But however, in the symmetric subspace, you have to really do the up plus down. Only this one state in the symmetric subspace space. And this one state appeared as a bulk topological order. not the other one. The up minus down is not there. It's not on the boundary of topology order. The boundary topology only simulate up plus down. Yeah. Yeah. Okay. So this is this really is a holographic picture, and but here I want to say the one thing. By looking at the symmetry only within a symmetric subspace, have a cost. Actually, is a so the cost is that sometimes two different symmetry behave the same within the symmetric subspace. And one example is a Z2 symmetry and a Z2 cross Z4 symmetry and a Z2 cross Z2 with a mixed anomaly in 1 plus 1D. And these two symmetry looks different, but within symmetric subspace, they are identical. They are indistinguishable. So actually there's a duality mapping. These two symmetry are called a dual equivalent, or we call hollow equivalent. And so therefore this using Bob topology order to describing symmetry is a little bit kind of not very detailed. And we only describe this hollow equivalent class of symmetry. So up to hollow equivalence is describing this symmetry. So we cannot distinguish Z4 symmetry and Z2 cross Z2 symmetry. And but however, actually this hollow equivalence is not too big deal if you want to using symmetry to constrain low energy dynamics. The claim is that the Z4 symmetry constrain low energy dynamics exactly the same way as a Z2 cross Z2 symmetry with a mixed anomaly. Means that the Z4 symmetric system have a same phase diagram as Z2 cross Z2 mixed anomaly symmetry. The phase diagram is the same. And the critical point is also the same. They all have one-to-one correspondence. So therefore, knowing one symmetry is equivalent to know another symmetry. So for example, this D-confined critical point can be understood this way. Like in Z4 symmetry, we have a from Z4 to Z1 transition, which completely breaks symmetry. And this kind of symmetry breaking transition correspond to this in a Z2 cross Z2 sense. You break one Z2, another Z2 unbroken. Then another phase is the first Z2 is broken, the second is unbroken. And this transition, there's direct transition for this. And this transition corresponds to Z4 to Z1 transition. So we can understand the defined critical point using this equivalent symmetry. Okay, but anyway, so the bottom line is that this bulk topology order, the bulk topology order, or maybe the Bragg diffusion n category, describe this hollow equivalent class of the symmetry. So this is a very general theory for symmetry, and we believe this theory covers all possible generalized symmetry. Okay, so therefore this classification of a topology order in the bulk became classification of symmetry, general symmetry in one lower dimension. And but certainly the symmetry little bit is only up to hollow equivalence. But not every bulk topology order corresponds to symmetry. Only bulk topology order with a gapped boundary corresponds to symmetry. And this the in mathematics called the with trivial class, the belong to trivial width class. The one with the gapped boundary is called belong to trivial width class. Okay. So here, this is a number of topology order with different type of onions. And then only subset, actually small subset, they have a gapped boundary. So those are small subset. So this basically classify the 1 plus 1 dimensional symmetry. Yes. Yes. Here is a condition, but will become data. In a sense, it turns out that if you include the boundary data, you don't need to. You can go beyond this hollow equivalence. If you ignore this gapped boundary, you only classify symmetry based on this hollow equivalent class. But adding this boundary as a data, you can resolve inside this hollow equivalent class. So that is that is yeah, that's another angle. Yes. So from here, let's see that this for example, when I have 4 onions, there's 18 topology order with 4 onions, but only 3 of them correspond to symmetry. So it means that in 1+1 dimension, we have 3 type of symmetry, which have the number of symmetry charge and the symmetry defect together is 4. So there's some symmetry charge, there's some symmetry defect. You combine them together plus their bound states, there are only 4 of them. And in this case, there's only 3 symmetry. So this 3 symmetry actually is the first one is the Z2 symmetry. Okay. And for Z2 symmetry, how we describe Z2 symmetry, actually, this one way to describe this symmetry is as we have a so-called local symmetry operator. So every symmetry is a selection for a set of operator we call local symmetry operator. We do this in a strange way. So for if you pick one-dimensional system called Z and Z, X and ZZ as a, so this is my local symmetry operator, and their product local symmetry operator. So what is symmetry? Then the symmetry is a commutant, you know. So the operator which commute with all the local symmetry operator. This commutant operator is a symmetry generator. And from here, when you define this local symmetry operator, the commutant operator just this one, this is the only one. And that you can see, oh, this is Z2 symmetry. The realization will be Hamiltonian just sum of this local symmetry operator in a certain way. So any sum will be symmetric Hamiltonian. Okay, so that's a wonderful symmetry. Then another symmetry actually is this one. The local symmetry operator is this collection. It's a ZZ still there, but the X is always accompanied with is a 3-spin operator, and with a minus sign. If you put plus sign, you need to put another Z here. I don't know what is the minimal generating set, but I think this is the one of a generating set of all the local symmetry operator. It turns out that the commutant operator is again is do the spin flip. X is spin flip, but plus some kind of a phase twist, which is not on site. Now the phase twist contain different sites together. So there's some kind of this kind of CZX. So this is CZ gate. The quantum information. This is a controlled NOR gate. This is the X. So this is kind of like a CZX transformation. Okay. And this one turns out to be anomalous Z2 symmetry. So this is a two of the 3 here. Yeah. The third one is interesting. The third one is okay. I want to say that the bulk topology order for the first Z2 symmetry, the bulk topology is a Z2 gauge theory. This is double Samyang theory. So this is 3. So one is Z2 gauge theory, and that's double Samyang theory. The third one actually is a double Fibonacci symmetry. So the bulk is a double Fibonacci. Okay. So that's another symmetry. And so this is kind of you know, what do you mean by this Fibonacci symmetry? So what is the realization? So it's hard to see it's a symmetry if you don't have any realization with that. And so here I want to say that this holographic picture also gave you a realization. And so you have a bulk Fibonacci topology order. Okay. And then this is a free sandwich picture. That is you can have this you have a bulk topology order, and then you have you have this because you want to realize a 1+1D system. But we start from 2+1D lattice, but a slab of 2+1D lattice. On this 2+1D slab, we realize this a double Fibonacci topology order. It's one of the stringlet states. Okay. Then this stringlet state double Fibonacci allow a gap boundary. So we put a gap boundary there. But however, this bulk and the gap boundary are high energy, maybe infinite energy. And the lower one is a lower boundary is a low energy boundary. So this is slab of 2D topology order is claimed to be realized as a Fibonacci symmetry as emergent symmetry. The low energy excitation are all given by lower boundary. The bulk and top boundary have a very high energy excitation. So that's a so can ignore. So only below this energy scale we get the emergent symmetry. So what is a symmetry transformation? Actually, symmetry transformation is given by the following. You know, the bulk topology order have a Fibonacci anion. This have this psi. Okay. And in double Fibonacci, so the psi is one of Fibonacci anion. Psi bar is another Fibonacci anion, but it's kind of complex conjugate. The topological spin is the inverse. Okay. And so one of a string operator which perform a symmetry transformation is this string operator creating a pair of Fibonacci anion. So you can see you have a bulk string operator which create a pair of Fibonacci anion. So when you apply this string operator to the bulk, that's also a transformation of this quasi 1D system. That's also transformation of this quasi 1D. So that is symmetry transformation. So basically, by applying this string operator, we actually performing the symmetry transformation in this string region. Yeah. And this one is non-invertible because this psi is a non-abelian anion. So two string operators together, you don't get a third string. You get a sum of two other strings, something like. So this is a example that you can have this emergent Fibonacci symmetry. So that is something beyond this. So this one is anomalous, and also it's also beyond the invertible anomaly I just described. So this is a very interesting example. So even Fibonacci symmetry is kind of strange symmetry described by this double Fibonacci topology order can be realized as emergent symmetry. Yeah, this I don't want to say no, this is anomalous. It's not an invertible anomaly we described before. Yeah, you can say it's non-invertible anomaly, but here anomaly just means not anomaly free. It's not anomaly free, but in addition, it's not included in the anomaly we just described. Yeah, so anomaly is a little bit tricky, and but this picture is a more this bulk topology order naturally include anomaly free, anomalous, invertible anomalous, and also beyond the invertible anomalous. So they all included there here. Yeah. So this is but again there's an open question here. You can see that this Fibonacci symmetry is realized as an emergent symmetry, not realized as an exact lattice symmetry. We have a lattice system only in the low energy subspace. We have this symmetry. And it's an open question whether Fibonacci symmetry can be realized as an exact lattice symmetry or not. I don't know actually. I think no, but I couldn't have a proof of that. Yeah, so we know anomalous symmetry can be realized as exact lattice symmetry. You know, it's just like this. You know, this lattice model they have this exact symmetry. So there's a lattice realization of this kind of anomalous symmetry. This is invertible anomalous symmetry. But the Fibonacci symmetry also anomalous, but it may have a feature which is not lattice realizable, but realizable as an emergent symmetry. So we start to see those very interesting feature of symmetry which you probably didn't notice before, but now this kind of exposed. So it's kind of an interesting direction to study. Oh, this boundary can be gapless. If they are gapless boundary, then this gapless CFT would be protected by Fibonacci symmetry. So there's certain. So actually, there's a in this paper, we have some in the updated version of this paper, which going to be posted soon. So we can apply this Fibonacci symmetry to study the gapless CFT and the critical point and multi-critical point. So this is why by study boundary of this box topology order is one way for us to study the CFT constrained by symmetry. Yes. Yes, and but there's several issues, and is that whether Fibonacci symmetry guarantee gaplessness, and or whether you need to fine-tune parameter to achieve gapless CFT. So there are issues there. Actually, it's a little more complicated. Okay. No, it's a construction. So the claim is that so here we claim we have a symmetry. So now I construct a particular one-dimensional system, which realize this symmetry as an emergent symmetry, as a low energy emergent symmetry. So this slab of a lattice is a 1D model, and they have high energy space, low energy space. The claim is that low energy space have this symmetry as an emergent symmetry. Yes. Maybe yes, I don't. Yeah, that's a very interesting question. And so, as definition, this low-energy space only have an emergent symmetry of this bulk. However, when you consider gapless boundary, the gapless boundary may have even more. Actually, that is the case. In this case, the double Fibonacci topology order is never a maximum emergent symmetry. So every gapless states have a more symmetry than double Fibonacci. And so therefore, it is a classification of this maximum topology order correspond to gapless states. If you start with a given symmetry, the gapless state usually have a more symmetry. And so there's a little bit of jump here. And but so therefore, there's a study of this so-called what kind of topology order can be a maximum symmetry will be interesting topic. So again, that's an open question. I don't know. You know, this topology order some British candidate. Then we say the British candidate are not equal. Some of them can be maximum symmetry, and some of them cannot be maximum symmetry. And what is the feature of a British candidate? You can say that. I don't know. Yeah, that's again open question. I don't know. Yeah, but maybe yes. Yeah, this again, I'm thinking about that. Actually, for the Z2 gauge theory, the Z2 symmetry, the bulk topology order is a Tor code have an EMA change symmetry. And in that case, this additional symmetry is stored in the bulk topology order. It's gauging the automorphism, the EMA change symmetry, you obtain the bigger emergent symmetry. So that's one idea. You gauge all the automorphism. Maybe you get something, you no longer have an automatic gauge. Maybe that's one idea to get this. But I talked to some people who, yeah, this thing is not well studied, so people don't have too much thought about this. Oh, I don't know whether this makes sense about even, but for Tor code model, it seems to work that way. Yeah. So that's really so I hope we can study this within this bulk topology order to see which one is the maximum symmetry. That would be really nice, but I'm not sure it really works. Okay, so maybe so I can go a little bit over half of my talk, but anyway, I'll finish it soon. And so as Dan already anticipated that. So here, in this case, we have this bulk topology order only describe this hollow equivalent class of the symmetry. Okay, and we emphasize actually now let me emphasize this. If you want to study gapless states, the hollow equivalent class is enough because the equivalent symmetry have the same constraint to the gapless property. So there's some feature that we don't have a detailed information of symmetry. Losing some information is more convenient. So if you want to study gapless state. Okay. But however, we do have this more information. Symmetry is we can go beyond this equivalence. We can describe symmetry directly, and really try to go beyond the hollow equivalence. And there's there's a theory for that. And so this is so maybe let me just say the following. You know, I just described this anomaly-free symmetry using this fusion category of a charge operator, of charge excitation. And this description is beyond the hollow equivalence class, you know. And so these are really described symmetry, not just up to hollow equivalence, but this is just a full description of symmetry. Okay. But this holographic I described is up to hollow equivalence. So now I want to go beyond hollow equivalence. So there's actually this kind of thing relate to this morphism between quantum field theory. Okay, so morphism in mathematics is a symmetry preserving map, like the map between two sets which preserve multiplication. That's the morphism of group theory, something like that. Okay, so here we want to map one quantum field theory to another quantum field theory, which preserve something. Okay, so we want to define morphism between quantum field theory. Okay, and we feel this morphism is very important because this structure preserving map is a very important concept. If you can generalize this concept to quantum field theory, it should be very useful. So that is really the motivation to do this study, morphism between quantum field theory. Okay. Yeah. Yeah. So here the point is the following. That's the structure we want to preserve is a local low energy property. So we say two quantum field theory are kind of equivalent if their low energy property are equivalent. So we want to therefore this is a little like duality. We have a two quantum field theory with the same low energy property. Then we say there's a morphism between two quantum field theory, which preserve low energy property. Yeah. Yeah. So here QFT can be gap or gapless. But the gap that means a bigger gap. They have same low energy property. I mean, both are gap or both are gapless. Means here there's a scale. So below certain energy scale, the QFT prime is the same. So means the low energy is identical. They have same mass, same number of gap or gapless mode. But however, there is something beyond certain scale, they are different. So basically, in some sense, it's really like that. It's really the following: you have two QFT, and we define two QFT are hollow equivalent. If you're stuck with a two hugely gapped system, then the two QFT became identical. Then we say this QFT are equivalent. So this local low energy property is a structure we want to preserve. So therefore, this morphism really try to preserve local low energy property. So basically, this gap means a TQFT. TQFT only contains the global very high energy behavior. So two QFT different by TQFT are regarded as equivalence. So using TQFT is this, but analytics you can have anything with huge gap would do the job. So this is may be the motivation. Okay. And then we develop some theory, which is really, but we think about the hollow equivalence between two anomalous TKFT, But anomalous means they're boundary of something, they're boundary of some topology. So this blue part as describing anomaly. So therefore we have a TKFT, which is a boundary of that. And then there's another TKFT. Okay, but these two TKFT only differ by a gap the boundary. But here is the main one, because the both TKFT are boundary of something, and we can add a gap the main one and get another topology order and get another TKFT. So then the claim is that these two TKFT prime and this TKFT here, they are equivalent. QFT, not QFT. The two QFT are equivalent. So here, this equivalence is given by this transparent domain wall. So this transparent domain wall means that the equivalence between this QFT and this stacking of this combination of this RMQFT. So basically, these two are equivalent. So this really define equivalence. So we call this isomorphic holographic decomposition. So a QFT, anomalous TKFT, not TKFT, anomalous QFT can be viewed as this stacking via some topology order with a gap boundary. So that is so this equivalence. But however, I think in this paper we view this equivalence relation from another angle as a morphism. So we view this domain wall in a boundary and that domain wall together, this pair as a morphism between two TKFT. Yeah. So there's some formal way to view the equivalence, turn the equivalence relation into the morphism. So therefore this picture really is formally is as a this structure is a morphism which map one QFT to another QFT. And there's some formal way to define morphism this way. Actually, this morphism became very interesting because suppose these QFT are gapped boundary. These QFT are gapped. Then the gapped boundary are described by the fusion category. So these two QFT for gap boundary, this became a two fusion category. And then this morphism between a morphism of a two fusion category. And my mathematical colleague showed that this morphism actually is a monodal Fourier function, a monodal function between two fusion categories. So so this definition became kind of interesting, but it's useful here because this also apply for gapless situation. And so how one explore this to gapless situation would be the interesting case. Okay. Yeah, here our system are here. The vertical direction is for the bulk. Yeah. Now you can go draw that vertically, but here, yeah, actually when you view this morphism, you can draw that vertically. So that means this is just go one to another side. Yeah. And draw this way is emphasizing this equivalence, means this one and these two are equivalent. So this really led to this sandwich picture. Yeah. And so if you for anomaly free system, the bulk is trivial. If you assume these two QFT are trivial, so the bulk is trivial. So QFT is trivial. The bulk is trivial. So there's no anomaly. So then you get this picture. So bulk trivial, then you have QFT. And then if this QFT have this decomposition, can be decomposed this way, then we say this QFT have a symmetry. Actually, this bulk M is the bulk topology order we just talked about. So therefore this boundary of M is anomalous. So we say anomalous symmetry, it really means this M. But however, this decomposition contains both M and R. There's other gap boundary. So therefore, we have another gap boundary. Is a more complete description of the symmetry. So this actually was this free Mott element on top of this sandwich picture, and you can stack this the system, any system with this which allow this decomposition would means it has symmetry. So actually, to discover a symmetry of the system is trying to decompose the system in such a way. When you find a decomposition, you find a symmetry. You find another decomposition, you find another symmetry. You can combine two decompositions, get even bigger decomposition, you get a bigger symmetry. So the process to calculating this decomposition is process to discover symmetry. So this really led to this this generalized symmetry. And here, one thing I want to say that this pair, this boundary and the bulk together is called a quiche, and that is a more detailed way to describe symmetry. And but here I also don't know whether Dan have any comment here. But however, there is a relation that because this boundary is a gap boundary, so this boundary is a fusion category, describe fusion category. And the bulk is a modular separated fusion category. But their relation, the bulk is determined the boundary. So there's a saying that maybe just this boundary, this fusion N category already describes symmetry. And but there can be some subtlety, whether how this fusion category and all this, but how they are connected, whether there's some additional data there. I'm not so sure. All kind of the context, and so maybe this I don't know whether this quiche actually not only contain rho and sigma, also contain information how rho and sigma connected. If that's what you say quiche, whether there's whether there's some data there or not, I'm not so sure. Yeah, that's a question. Yes, but however, the question following, because the sigma is determined by rho, maybe you can drop the sigma. I see. Okay, I see what you mean. So maybe I know what you mean. Yeah. So right now, so the question following, whether you can view rho like in 1+1 dimensional boundary, should one view rho as a fusion category? Yeah, that is the question. Whether view is a fusion category. So the statement here will be like in 1+1, the generalized symmetry, they are described by fusion category. Every fusion category describe a symmetry, general symmetry. Then it's a local fusion category describe this anomaly-free symmetry. The general fusion category would describe symmetry. That would be the picture. And so actually, when I'm using this R tilde, I'm using this language. This R tilde have two meanings. One is describing this gap boundary. Another meaning R tilde is actually a fusion N category, describing the fusion of a boundary extension. Is a fusion N category. So the claim here is really that there's the general symmetry are classified by fusion N category, and applied to one dimension is a one-dimension generalized symmetry is classified by fusion 1 category. That is the statement. So, but anyway, so this is so this really led to some general picture of the symmetry, and so the point is that this really represents a holographic picture to view symmetry. So we have a system, we have decomposition, and we have a bulk, we have another boundary, and those really give us information of symmetry. So right now I try to turn everything into this picture, so understand all the symmetry in terms of this picture. and not try to say anomaly, because anomaly is very confusing. But this picture is more general. Yeah. So so I think this is the natural place for me to stop, so we can get this general theory for general symmetry, and certainly other we can apply this picture to study many physical situations. Yeah. Okay, yeah, maybe we can do that. Yeah. Thank you. Yes. Yeah, but I always prepare too much. But yeah, later there's I think this is just a general framework, and then later I will try to describe some application of this framework. Yeah.
Since there's no question,
yeah, I can continue. Yeah, but really feel free to leave. Yeah, this is just I think I take too long. I was hoping I can finish this time, but still couldn't. Yeah, and so there's yeah. So yeah, I think the good thing to let's make a record so we can. There's online, you can read online. Yeah, and so this so anomaly free. So now let's go back to this anomaly free symmetry. What is the anomaly free condition? Using holographics, how to describe anomaly free symmetry? Okay. So here I'm using the other language. Using this language. So now we're describing symmetry using this fusion N category. This fusion kind of sounds scary, but actually it's just a fusion of this symmetry defect. Like when you have this Z2 symmetry, the symmetry defect just a Z2 symmetry domain walls, and you can fuse two domain wall to get another domain wall, and so this Z2 symmetry breaking domain wall just some kind of fusion N category, and a formal name called the VEC G, you know. So this is this is a fusion category, and but now the question that you know, when you only do fusion N category, they can be very general, and some of those symmetry can be anomalous, and some of them are anomaly free. So the question is that which one is anomalous, which one is anomaly free? So that is the question. Okay. So how do we know that this R tilt always describe the fusion of a symmetry defect? The different from R I used before. R describe the fusion of a symmetry charge. Yeah. Okay. So now the question that given the fusion category of a symmetry defect, can we identify which one is anomaly free, which one is anomalous? So that is the question. And then it's really this picture. The given R tilt, if you have another fusion N category, such that this stacking became trivial, then that is anomaly free. So so this So therefore, under this condition is very much like what we in this picture. Remember, this picture really represents a quantum field theory with a symmetry. Choosing this lower boundary to be R is like choosing the symmetric product states. Okay, so the symmetric product states and means when you're choosing R is like choosing ground state to be symmetric product states, and the symmetric product is a trivial. Yeah. So therefore, if you have a symmetry which allow this boundary, which can be viewed as symmetric product states, then that means this symmetry is anomaly free. It's actually from definition. Anomaly free means it allows trivial symmetric product states. And so then that is the condition. So therefore, an anomaly free symmetry also have the condition. If the R, maybe let me put it this way. If R tilt, there exists R such that this composition is a trivial states. Then this fusion N category is a local fusion N category. That's definition of a local fusion N category. Okay, yes. Do not have any symmetry. So yeah, it's just like a product states. So this is so that is this really means there exists the, let me see. Yeah, you can say this trivial state have a symmetry, have a degeneracy, but you don't look at the symmetry. I mean, yeah, I don't know what to say. It's means you have an operator which breaks symmetry, but you do not commit it. You don't add this operator to the Hamiltonian. So this is still, I still have some issue how to understand this. So this trivial product really means that okay, let me say on this boundary, you cannot add the operator which is split, say this spin 1/2 degeneracy. On this boundary, you cannot do that. But however, when you combine these two boundaries into this boundary you allow this operator which is split degeneracy. So what really happens is really following. The operator which breaks symmetry are connecting the two boundaries. When I draw this way, we say these two boundaries very far away, we do not allow this operator. Then that means we have a symmetry. But when you draw this way, then this operator is allowed, but we may not commit it. We may not add to the Hamiltonian. This operator is allowed as a probe, maybe not in the Hamiltonian. Yeah, so there's some. So this picture means a lot, and so we are still kind of explore what the really meaning, what's all kind of meaning of this picture. Okay, yeah, no, that's a key, because some operators are allowed, means they can be potentially added to the Hamiltonian. When you construct patch operator, you include all those allowed operator. Yeah. So the allowed operator here and here are different. The allowed operator here just operator act on the boundary. The allowed operator here are operator act on the boundary, also operator act between boundary and also string connecting to boundary. All those are allowed. So when you construct patch operator, you have more thing to yeah, you have more blocks. You can put the more things together. Yeah. Okay. So this really the connect these two things. And then I want to say that remember I just mentioned that this R tilt is a fusion category of symmetry defect. But this R actually is fusion category of symmetry charge. So this symmetry is R and R tilde. This form a dual pair. You know, the symmetry defect. This is symmetry charge. Okay. And this is a picture to get the anomaly. You again use a holographic picture. You can describe anomaly. So the idea is that now the R I'm using the symmetry charge. Now R here is the symmetry charge. Okay. When you have anomaly-free symmetry, you know, anomaly-free symmetry is described by R tilde, the fusion of symmetry defect. But there exists local fusion category R, describing symmetry charge. For anomalous symmetry, we don't have that R. For anomaly-free, we have this R. But once you have R, for anomalous symmetry, we can gauge that. How to gauge that? The idea is that if you usually for the group symmetry, if you gauge the symmetry, you get topological order, which is described by gauge theory. So here I want to say we have a fusion category described by R. Then if you gauge that, you should get topological order. This topological order corresponds to gauge theory. So the R gauge theory. But this topological order is obtained this way. We have R, it have a bulk. There's a bulk symmetry TO. Then another boundary is also R, but in a different orientation. Yeah. And because this structure, this slab is R gauge theory. It works. Actually, if R is a group, so this R is a rep G. This is also rep G. And in the middle is a G gauge theory. And then you put together, then you'll find that this slab describes a G gauge theory in one lower dimension. So like a dimension reduction of a G gauge theory. You have a higher dimension G gauge theory. You have one boundary is a rep G boundary, another boundary also rep G boundary. Then these two boundaries together give you a gauge theory in one lower dimension. So there's dimension shift. However, just a moment. However, if you put the R tilde here, if you start a gauge theory, you put the R and R tilde there. This slab is a trivial state. So the gauge theory can be reduced to trivial state if you put the R tilde. So you put the rep G and the vec G as two boundaries, you get trivial states. But if you put the rep G on two both boundaries, you get a one lower dimensional gauge theory. Yes. Probably it means I think let me see. It's does not mean conjugation. I think it no means that. Okay, let me put this way. If I do this, I can connect these two very easily. So it's indeed means the complex conjugation. So the spin get reverse sign. Yeah, because this thing you can unfold this. Yeah, unfold this. It's just one boundary. It's unfolding back. It's actually much better for me to do this way. And so this is gauging. So again, this is an interesting question. You know, for more general symmetry, and we have fusion category. We have just a fusion category of a charge or defect. What do you mean by gauge that symmetry? Well, here's a gauging. And but then once you know gauge theory, then we know how to define this invertible anomaly. We just add a cocycle twist. You know, the diagonal vision theory means we start with gauge theory. We twist it by some cocycle. So here's same thing. We have a gauge theory. We twist it by something. Then we get a twist in the gauge theory. And the boundary of a twist gauge theory will describe an anomalous symmetry. So that's exactly the same idea. So here the cocycle twist is this dotted line. Is a automorphism. if this bulk theory have automorphism, we can add automorphism, then that's a twist. It's actually co-cycle twist, I think, may have this interpretation. Okay. And so this is the idea. The sigma really about the dimension, because suppose we have a symmetry R on this boundary, so that's R. But however, this gauge theory is for the symmetry R in this line is a one higher dimension. When you have a group symmetry, it's easy. The group symmetry at the one dimension is same group symmetry at two dimensions, the same notation. But here, when you have a symmetry described by R, R is the fusion category of a charge. The same R at a different dimension of different notation is really the sigma. And so we have a symmetry of R charge at a one lower dimension. In one higher dimension, that R became sigma R. It's delooping. You just add this one layer. But anyway, this is kind of technical. And so that's a sigma is really, we want to go symmetry here, but we have to go increase one dimension, then consider this higher dimensional symmetry and their gauge and the automorphism is here, the dimension shift and both sides. And then what is the symmetry of this boundary? So this may be actually a research project. That is maybe because this is part just symmetry TO of this anomalous symmetry. So we know the symmetry TO of anomalous symmetry here, or here, maybe here. This boundary have an anomalous symmetry now. The symmetry TO is this gauge theory, but with the inserting of this automorphism. But what is the other boundary? Then another boundary naturally is this. You can connect these two R, and then this and then this automorphism should preserve this boundary R. But anyway, this is something. Yeah. So this is a situation. Yeah. So you need to leave? Yeah. Yeah. Okay. Yeah. So let me just but here is something we struggle with. That is using local fusion N category to describe symmetry seems to have a problem. That is the problem is that because this boundary can be a topological order, just a topological by itself. The topological order state is a boundary of trivial states. It's a boundary of trivial states. And this topological order is a fusion category. Do we view this one as symmetry? Because this bulk is trivial, then this boundary have no constraint. So this boundary, you can add any local operator to this boundary. So that's like a situation with no symmetry. Any local operator, no constraint, anything is allowed. But using the pair language, this anomaly-free topological order plus the trivial bulk, this pair is a symmetry. But this symmetry, in this case, this symmetry means no symmetry. So it's very confusing. Okay. And so maybe it's okay. Maybe mathematically it's natural and okay to call this a symmetry. But physically it's very strange. This symmetry provides no constraint to the boundary. So in physics, there's some wish. We do not call every fusion N category symmetry. Maybe only some of them are symmetry. Okay, actually, there's a local fusion N category is one way to do some of them. Actually, local fusion N category always have non-trivial topological order. So it resolves this problem. But we also know that the local fusion N category is too restricted. It describes anomaly-free symmetry. They do not include the anomalous symmetry. But the fusion N category is too broad, including this trivial case. So this again is an open issue. So which fusion N category actually describe reasonable symmetry in in physics. So this is another open issue. Yeah. And one proposal is that the following. If we can say that the two fusion n category have order, we can say small or big. If R prime, this fusion category can be viewed as a fusion category R, starting with a topology order, anomaly free topology order, then this is then we say R prime is less than R prime is bigger than R. Then we define this order. Then using this ordering, you can define the minimal fusion n category. Then this minimal fusion category probably define this topology symmetry pattern. So this is really the idea. Then using this concept of minimal fusion n category, we can get a general result for symmetry protected gaplessness. So the symmetry protected gaplessness is really the following. There's a three type of symmetry protected gaplessness. And because when we say symmetry protected gaplessness, we have to make some condition on the states. We say this state have a symmetry. If it's an arbitrary state, maybe there's no symmetry protected gaplessness. So usually symmetry protected gaplessness means that symmetric states must be gapless. There's certain symmetry that a symmetric state must be gapless. So that is symmetry protected gapless. But however, the meaning of symmetric state became very tricky. What do you mean by symmetric state? What do you mean by state which do not spontaneously break symmetry? It's became very tricky concept. So one way to describe a symmetric state is following. The state are basically a boundary of this bulk topology order. One way to define symmetric state is that the bulk anion do not condense to the boundary. There's a particular boundary where nothing condenses. And this particular boundary, because no bulk anion condense, we say this state preserve the symmetry TO, preserve this holographic symmetry, this symmetry bulk topology order symmetry. In this case, every symmetric state is gapless. We can prove kind of prove that. If you do not allow any anion condensation, this is then this unless no symmetry, then every symmetric state is gapless. Okay. So this language is very special in a sense. It describes this how this really tell us the gaplessness on the boundary is determined by the bulk topology order. So give us some kind of insight that the topology order determine the gaplessness. And so maybe this way for us to use this to describe gapless states. Okay. Then however, there's a type 2. Type 2 is that we include this boundary. Then when we say this boundary is symmetric, means they do not break this symmetry. So we do allow some condensation, but this condensation do not break this symmetry. This describes the fusion category. So what do we mean by that? Remember, this boundary is the extension of this boundary is a symmetry defect. And this boundary is obtained by condensing the symmetry charge. For example, if M is a gauge theory, the gauge theory have a gauge flux and a gauge charge. And this boundary is condensing gauge charge. This boundary. Okay. So this is intrusion. So this R tilde boundary is about obtained by condensing symmetry charge. Whatever condenses on this boundary, we call symmetry charge. So therefore, not breaking this R tilde symmetry means that if something condenses on the top boundary, that kind of thing cannot condense on the lower boundary. So the condensation of the top boundary and the lower boundary cannot have overlap. Nothing condenses on the both boundary. And if the lower boundary have that property, we say lower boundary do not break symmetry, described by R tilde, not symmetry TO. So this really symmetry are two. The first type one is a symmetry TO. They do not break symmetry TO. Here they do not break symmetry. That's type 2. And so this is a more Euro situation. It turns out that we have argument that the symmetric state must be gapless if and only if this symmetry is anomaly free. Yeah, this sounds strange because we have counter example. We know that anomaly free symmetry allow gap the topological order state which do not break symmetry. We have an example of that. But here there's a more general example. We have different conclusion. Yeah. And so the resolution is falling. I think maybe there's again the open issue. Is that the previous example of an anomaly-free symmetry, which allow gap symmetric states, all have a space-time symmetry. And here we only discuss the situation with no space-time symmetry. Okay. So yeah, so this relates to what we talk about. You know, adding space-time symmetry is non-trivial. It's something extra. So here the conclusion that if our symmetry do not involve in space-time symmetry, maybe this is correct. The internal anomaly-free internal symmetry must be their symmetries must be gapless. This may be a valid statement. So that's something we can explore. Yeah. Yeah, the finite, certainly finite. Finite also important. This is also about the finite. And for infinite symmetry, there's other issues. So this really led to the situation that indeed we have very good, this anomalous definition is pretty good. So this anomalous protect symmetry in such a very unified way. But however, if you have space-time symmetry, we need to have the holographic theory for space-time theory separately. And in that case, what do you mean by symmetry product gaplessness? Maybe there's other meaning. Meaning can be different. Yeah. Okay. And there's a third type. The third type anomaly-free symmetry is that this works. I did not note it. It works that for continuous symmetry, things can happen. The system with the continuous symmetry with certain anomaly must be gapless, regardless which state they have. Even symmetry breaking state, whatever states. This symmetric Hamiltonian always gapless. So that's a type 3 I did not discuss here. Okay, so maybe I think I should really stop here. It's too long, but this is really I think a nice point to start. So you have this. You see that how the symmetry anomaly free and they really impose some general condition on the gaplessness. And so this theory is not complete yet, but we see something some direction. Yeah. Yeah, I think yes, I should do something. Yeah, but I think the later you say I think okay, it's more familiar with yeah. Thank you.